Hi all, welcome to a new video. This video is about the metal oxide semiconductor field effect transistor, that is the MOSFET. And in this video we'll be mainly discussing about the functioning of an N-channel enhancement type MOSFET. Before that we'll just briefly go through the types of MOSFET and all, but since NMOS is the most widely used type of MOSFET, we'll discuss in detail about the functioning of N-channel enhancement type MOSFET in this video. So let us begin. MOSFET is also known as insulated gate field effect transistor, that is IGFET. The reason behind this is that there is an additional layer of SiO2 fabricated on the gate terminal of the IGFET or MOSFET. That is why it is known as an insulated gate FET. But in the case of source terminal and drain terminal, this layer is not there. There is direct metallization of the substrate. So that is why it is called an insulated gate FET. Now basically MOSFET can be classified into two, that is N-channel MOSFET and P-channel MOSFET. In the case of N-channel MOSFET, the channel will be mainly of the N type, but the substrate will be of P material, but the channel induced will be N type, that is the majority charge carriers will be electrons. But in P-channel MOSFET, the substrate will be of N type material, but the channel will be P type and the majority carriers will be holes. Okay, so since electrons are having a higher mobility than holes, the N-channel MOSFET will be having a better high frequency response and will be performing at better high speeds. So that is why N-channel MOSFETs are widely used. Now, depending on the mode of operation, MOSFET can be classified into two types. First is the enhancement type MOSFET and the second is depletion type MOSFET. The depletion type MOSFET is also known as depletion enhancement type MOSFET or DE MOSFET because it can be operated in both depletion mode and enhancement mode. But the enhancement type MOSFET operates only in the enhancement mode. And this is the widely used MOSFET technology, that is the E MOSFET, that is the enhancement MOSFET. So we'll be discussing about the N type enhancement type MOSFET here. So let us first see what is the basic difference between E MOSFET and D MOSFET. In the E MOSFET, there is no physical channel fabricated into the substrate. Okay, during the fabrication process we are not fabricating a physical channel between source and drain in the case of an enhancement MOSFET. The channel is induced by a positive gate source voltage, and for that you need a minimum value of gate source voltage, which is known as the gate source threshold voltage or VGST. So when the VGS is 0, ideally there is no channel existing between source and drain. That is why this device, that is the E MOSFET, is known as a normally off device. Okay, no, it is normally in the off state. But in the case of a depletion MOSFET, we are physically fabricating a channel in the device during the fabrication process. So we are having a conducting channel even when the gate source voltage is 0. That is why the device is said to be in normally on state. Here we will be discussing only about the enhancement type. So we'll move. Okay, so now let us see the working of N-channel E MOSFET in detail. First let us see the cross-sectional view. As you can see, there is a substrate of the P-type material and two wells of N-type material is formed onto the substrate. And these wells are actually made of heavily doped N-type material. So you can also represent it as N plus wells. Okay, and those forms the source and drain of the MOSFET. And in order to take the source contact and drain contact, a direct metallization is done over the wells and you take out the source contact and drain contact. But in the case of gate contact, there is an additional layer of SiO2 between the metallization and substrate. That is why we say this as insulated gate FET. This SiO2 forms the additional insulation layer in the gate. So this is the basic cross-sectional view. As you can see, there is no channel in the device, which is. Now we move on to the operation modes of N-channel E MOSFET. So as you have seen in the cross section, without any bias, there is no channel in the device. So you can consider it as two back-to-back PN junction diodes with the resistance of substrate connected in between. Okay. So there is no gate source voltage and drain source voltage. So the device will be in off state and can be considered as two back-to-back diodes with a resistance of substrate in between. Also, you have to keep in mind that there is always an internal connection between the source and the substrate. That will be done within the device itself. There is always an internal connection between the source and substrate. Now let us see what happens when you apply a positive gate source voltage. That is, you have applied a voltage such that the gate is positive with respect to the source. What happens? The negative charge carriers, that is the electrons, will be attracted towards the gate terminal from the substrate, isn't it? So those negative charges start accumulating near the surface of the substrate. Thus, you can consider that a channel of the electrons is formed near the surface of the substrate between the source and drain. You can see in the figure, that is how a channel is induced by a positive gate source voltage. Now, even though a channel is formed, the current has not yet started to flow because we have not connected the drain terminal. So, a conducting channel is formed and the majority carriers in the conducting channel are electrons. So, if the majority carriers are electrons, we say the material is N-type, isn't it? So, the channel can be considered as N-channel. That is why the name N-channel MOSFET. Okay. So, this N-channel can also be termed as an inversion layer because comparing to the substrate, this layer is just the opposite of it. So, this N-channel is also known as an inversion layer. Now, for this channel to be formed, this VGS has to be above a minimum threshold value, and that value above which the channel is formed is known as the gate source threshold voltage, VGST. Now again, we are going to connect a positive voltage to the drain with respect to the source. Okay, a VDS is applied such that the drain is more positive with respect to the source. So what happens? The current starts flowing from the through the conducting channel. The electrons will be flowing from the source terminal to the drain terminal because the drain terminal is positive. So the electrons will be attracted towards the drain end. So the electrons will be flowing from the source to the drain. Therefore, the current direction will be indicated as from drain to the source. We always indicate the direction of current to the opposite direction of movement of electrons. Okay, so the current will be from drain to source. So when VDS and VGS are applied, a current will be flowing in the device. Now let us see what happens when we increase the value of VDS. As you increase the value of VDS, the value of current will also proportionally increase initially. And this region of operation is known as the linear region of operation or the ohmic region of operation. But as you keep on increasing VDS such that it is more positive than the gate, what happens? The electrons will be more attracted towards the positive terminal of drain rather than the gate. So what happens? The shape of the channel will start to change. The channel will start to become narrow towards the drain end. Okay, it will no longer be in a correct rectangular shape. Instead, it will become narrower towards the drain end. And at a particular voltage known as the pinch off voltage, the channel will be completely pinched off at the drain end. This voltage is known as the pinch off voltage. Okay, at that point, the gate source voltage will be just one threshold above the VGST. Okay, so this voltage is known as the threshold voltage. Pinch off voltage. At this voltage, the channel will be completely pinched off at the drain end, and there will no longer be an increase in the drain current even though you increase the VDS. Now this mode of operation where the ID remains constant with respect to VDS is known as the saturation region of operation. So now let's move on to the characteristic graphs of the device. Now this is the drain characteristics of N-channel enhancement MOSFET. As you can see, there is a linear region of operation and a saturation region, and the horizontal axis, that is the x-axis, corresponds to the threshold value of gate source voltage where there is no current flow ideally. So that is the threshold voltage of gate source. Now next is transconductance curve of the enhancement MOSFET N-channel. Now last we'll see the common symbols of N-channel enhancement type MOSFET. Thank you.